Welcome, Regents students. Today we begin our next and final topic in our physics course. The topic is called modern physics. You may notice that the word modern is in quotation marks. I put it in quotation marks because some of the material that we're going to be learning was discovered in the early 1900s. Some of the more recent material was discovered in the 1970s and the 1980s. So for you wouldn't consider something from 1900 as being modern, but from a standpoint of physics, it is considered the modern era. So that's why I put the quotation marks there. Before I begin and jump into today's topic, I just want to say some general remarks about the material, the knowledge included in this topic. Some of it turns out to be extremely fascinating. So fascinating that, in fact, lay people, not physics students, not college students, sometimes buy books on physics. And I'm not talking about books that include problem sets and homework problems. I'm talking about books that deal with things, what's called quantum physics, which is included in this topic. We'll be learning a little bit about it. Why would they do that? Well, you yourself may have wondered at times if there was such a thing as fate or destiny. Maybe you wondered, is there such a thing as God? Or what is the nature of reality? Or maybe you discuss these kinds of questions with your friends. It turns out that quantum physics, which is included in modern physics, has discovered things with deep implications to those kinds of questions. Fascinating stuff, surprising stuff, revolutionary knowledge. And that's why people buy books on the topic. Now, of course, the Regents doesn't go into such questions, but I'm going to put in some extra information when I can, because for me, I find this stuff very interesting. And also, I like to, rather than give you just like the surface presentation that's in the Regents curriculum on the reference table, I want to hopefully give you a little bit more rich knowledge with the understanding of why some of these things happen. So some of the quotes here kind of get at the heart of what I was saying about the fascinating nature of the knowledge. But I'm going to skip over them today because they fit better into what we're going to be learning tomorrow. Today, we're going to be learning about photons. Okay? So, we learned in the waves topic that if I turn on a light bulb, it produces electromagnetic waves, or you could say electromagnetic radiation, and the waves are transverse waves with crests and troughs, and they radiate out all into space. Okay? Well, it turns out that that is not an accurate view. There were experiments and things that light did that did not make sense in terms of it being a wave. So basically, physicists need to come up with a new theory of what light actually was. The person who came up with the theory is actually Albert Einstein. He basically came up with the theory that light sends out not smooth waves, but things called photons. And a photon, I put it in quotes here because it's not really, that should be B-U-L-L-E-T. Let me just get an eraser. Hold on. Because, I put in quotes that a photon is a tiny bullet of light because it's a rough analogy. You could think of it as a little tiny submicroscopic bullet, something you can't see or feel, but think of a light as almost like a machine gun shooting out bullets in all directions. Now, in the case of bullets, they have momentum. If I take a block like this and I shoot a gun or a bullet into here, the block will start sliding because the momentum of the bullet goes into the block, and so it starts to move. So as with bullets, Photons, which are also like little bullets, they have momentum, lowercase p. And the magnitude of the momentum is given by a constant h over the wavelength. Or if you know the frequency, you can use this formula. H, I wrote it here, 6.63 times 10 to the minus 34 joule seconds. But as with all the numbers that you need or constants you need in the physics curriculum, it is on the reference table, front cover, right here. Okay, so we have this, table of information like G for gravity and all that. So down here we have Planck's constant, H 6.63 10 to the minus 34 joule seconds. Okay. Also, the speed of light here, as you know from the optics unit, it's right here. And by the way, 3 times 10 to the 8th, it should really say the speed of electromagnetic radiation, because this is also the speed of X-rays, gamma rays, radio waves, microwaves, all go at this speed through a vacuum. So that's the momentum of these little microscopic bullets coming out of a light bulb. And then also bullets have kinetic energy, 1/2 mv squared. Same thing with these photons. They have kinetic or energy equal to that same constant times frequency, or if you have the wavelength, then you use this formula. That formula for the energy of a photon is in the reference table in the modern physics section. You see E equals HF equals HC over lambda. Now, I forgot to mention this, but notice how I draw these photons as little circles. They're like little ovals, I guess. They're flying like little rocks or whatever flying, but they also still act like a wave. A photon, that's why I put it in quotes, it's much more complicated. It's neither a particle or a wave. It's something somewhat in between. So that's why I still draw crests, and I drew crests and troughs within that. That's my own little representation of a photon. So it's like a bullet, like a particle, but also it does have wave properties, has both. That's why I draw the photon that way. All right, so the first example, what we're going to do is we're going to calculate or determine the energy of green light. And remember, green light, if you look up on the electromagnetic spectrum on the reference table, green light is between 6.1 and 5.2 times 10 to the 14th hertz. Anything that has that frequency, any electromagnetic wave, if it goes in your eyes, you will see or perceive the color green. So I picked 6, which is between those two colors. And what I want to do is figure out the energy of that light, of that photon, I should have said, energy of the photon in joules, and then in something else called electron volts. I'll explain what that is in a minute. Okay, so the first thing, the energy, I just used the formula E equals HF. I get Planck's constant off the reference table, right? So that's, as I said, front cover right here, Planck's constant. So I jot that in for H, and then I plug in the frequency, and I get the answer, 3.98 times 10 to the minus 19th joules. Now, that's a tiny bit of joules, okay? So that's less than a millionth, less than a billionth, less than a trillionth. There's not even a word for it, how minuscule that energy of the photon is. To give you a sense of how small that energy is, what I have here is about a gram of milk in that little blue plastic tray. 1 gram of milk, to raise it 1 degree Celsius, which is roughly 2 degrees Fahrenheit, takes about 4 joules. So my point is that this is definitely too small for you to feel, okay? If I were to put this in my hand here and it was 70 degrees milk, and in the other hand I put the same amount at 72 degrees, I wouldn't even be able to tell the difference or perceive that 2 degree difference. So, and that's not much liquid. So 4 joules is already a pretty small amount of energy. less than a billionth, less than a trillionth of that is the energy of this microscopic photon of a green light. So if I had a green light bulb, it's sending out all these bullets, right? I put my hand here. I don't feel like if I was shooting with ping pong balls, I would feel them hit my hand. I would feel each discrete collision of the bullet of the ping pong ball hitting my hand in my nerve cells. But with this, so much energy, if one photon hits me, I can't even feel it. What I need to do is turn on a green light bulb and have not millions, not trillions, not even, I ran out of words, cajillion, I don't know, countless photons hit my hand, and then I would feel a warm, gentle glow. So this is why when you turn on a light bulb, you don't feel the bullets hitting you. Each bullet is minuscule. You need countless of them to hit you continuously, and then you perceive a very slight warm sensation. You don't feel the boom, 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 boom over and over again. Okay? So we don't feel the photon nature. And you might be saying, well, then it's irrelevant. Why do we even care about photons? Well, it turns out that the photon nature, the bullet nature of light or electromagnetic radiation can have severe consequences. What do I mean by severe consequences? Like life and death. Okay? So I turned on this light bulb and the light's hitting my hand. No one would be saying, oh, that's dangerous. Light is hitting your hand. So light normally isn't dangerous. And why is that? Well, the frequencies of the light rays are small enough such that when I plug these values in for the energy of these microscopic bullets hitting my hand, they don't hurt my hand. Again, the analogy would be like if I'm standing here and this is my stomach and someone's shooting a ping pong ball gun into my stomach, they could shoot me with one ping pong ball, 1,000 ping pong balls, 1,000,000 ping pong balls, and the balls will just bounce off my stomach and do no damage. But if I increase the frequency higher and higher, okay, then these bullets gain more and more energy. So if instead of shooting my stomach with 1,000 ping pong balls, if I shoot my stomach with one bullet out of a high-powered rifle, one bullet kills me, right? So that's not what's going to happen with a photon where one hits you in the stomach and kills you. But what they do is they hit your cells, your skin cells. And if they have enough energy, in other words, if they have a high enough frequency and we go beyond visible light and we go into the ultraviolet light, then that microscopic bullet comes and hits my skin, and what can happen is it can damage the DNA in my skin. So the little bullets of the normal visible light are not strong enough to go into my cells and damage my DNA. It's like the ping pong ball. My cells get hit and it's not fatal. But one ultraviolet light goes into my hand. If it hits my DNA just right, it can distort it and cause cancer. So that's the mechanism of what's going on with sun tanning. You go out and you get blasted with sunlight, which includes UV light. It damages your skin, and then when your body heals, it tries to produce the dark color to protect itself from the next time you go out in the sun. But of course, it's a game you're playing by going out, tanning, and then eventually you might get hit just right with just one photon, hits you just right, and then it could cause skin cancer because of the maiming. The photon has enough energy to maim the DNA in your skin cells and cause a mutation and incessant reproduction of the cell, which is a tumor, which can lead to a fatal condition. So photons, okay, it helps us understand what goes on with skin cancer and also other kinds of cancer, like when you go for an x-ray. You might notice if you go to a dentist, for example, They cover your body with a lead blanket because they don't want the radiation to go everywhere. Yes, X-rays, even more. They're a higher frequency, right? So the bullets of the X-rays are even more dangerous than if you go tanning. So it's a dangerous thing to get an X-ray, which is why we don't do them often. We only do them when it becomes medically justifiable, like when you're injured or something like that. All right, so that was a little aside about photons and the dangers they can pose. But look at this, a small number, okay? And it's kind of like the joule is too big of a unit. It's inconvenient for measuring the energy of a photon. Let me give you an example. Let's suppose I need to cut a little bracket to hold this pencil. And I say to somebody, okay, measure the pencil for me so I could cut the bracket the right size. And someone says, okay, I got the measurement. It's 1.5 times 10 to the minus 5th miles. I would say, oh, come on, stop being a wise guy. Don't tell me in miles. Tell me like in inches or something like that. And you say, okay, 6 inches, and then I could cut it, right? So the mile is like a silly unit to measure the length of this pencil because it's too big and this is too small. So the energy of this photon is too small and the joule is too big. So we invent another unit, kind of like instead of miles, we go to inches. Well, instead of joules, we go to something called an electron volt. An electron volt is literally the amount of energy you get when you let one single electron pass through a 1 volt battery. So the formula, right? Voltage equals work over charge. So if we have a 1 volt battery and 1 electron and we multiply, we get the energy in terms of 1 volt, 1 electron volt. So that's a tiny minuscule amount of energy. 1 electron passing through a 1 volt battery. So we want to convert to electron volts. So we take our old energy here in joules and we multiply by a conversion factor. We've done this before, but we need to, so we multiply by a ratio. What we have is oops, I put the joules in the exponent. I don't know why. Okay. So I multiply by a fraction, I put joules in the bottom and electron volts in the top so that the joules go away, leaving me electron volts. What numbers do I plug in? Well, I go to the front cover of the reference table and I see the conversion factor. So here is that table that we just used for Planck's constant. Right here I have 1 electron volt is equivalent to 1.6 times 10 to the minus 19th joules. So there's the ratio, 1 to 1.6 10 to the minus 19th. So with the joules, I put the 1.6 10 to the minus 19th, and then the 1 with the electron volt. And then, you see, as I said, the joules cancel and leaving me with electron volts. So I take this number, multiply by 1, and then divide by 1.6 times 10 to the minus 19th, and I get 2.49 electron volts is the energy of that green light photon. Okay, so just a little conversion. Now I also want to point out sometimes the problem works in reverse, as we've seen many times in this course. Maybe they give you this, they say a photon has 2.49 electron volts and they ask you the joules and then the energy. The way you would do that is you would do the conversion. Instead of putting EVs on the top and joules on the bottom, I now put joules on the top and EVs on the bottom so that the EVs cancel, leaving me just joules. So now I take 2.49, multiply by 1.6 10 to the minus 19th, and divide by 1, which gives me this, right? And then I could plug that in over here, 3.98 times 10 to the minus 19 joules. Plug in Planck's constant. This is unknown F. I divide and I get this. Then I go back to the reference table and I say, okay, now what color is that? I look up 6 times 10 to the 14th. Here it is. Oh, green light is the answer. So that would be the same calculation done in reverse. All right, so that's basically what you're going to be using primarily on the homework, that calculation. I want to point out one other phenomenon regarding photons that's sometimes in the curriculum. It's called the Compton effect. Okay, so what happens in the Compton effect is you get an X-ray photon, It's moving 3 times 10 to the 8 like all light, and it's a little bullet. That's what we said, that's what photons are. It strikes an electron. Now imagine you're playing billiards at a pool hall or something. You hit the cue ball, and this is like the 8 ball. What'll happen is the cue ball will ricochet going off in one direction, and the 8 ball will go in another. It's like a 2-dimensional collision. Alright, so that's the Compton effect. And what happens is this X-ray photon, in a collision, it's going to lose momentum because the electron gains momentum, right? Momentum's conserved. So if this gains, that has to lose so that the system has the same amount of momentum. Also, from an energy standpoint, this is going to have 0 kinetic energy, suddenly it has kinetic energy. How does that happen? Well, if this gains energy, this has to lose energy. So, how does the photon lose energy? Well, it can't slow down. Light always goes 3 times 10 to the 8 meters a second. So how does a photon lose momentum? Well, if the momentum decreases, the wavelength has to increase. So the wavelength increases and the frequency decreases. Now, another concept that's in, so that concept that the wavelength has to increase because of the collision in that X-ray. That's the concept, or in the Compton effect. Also, that the maximum increase in the wavelength is for if this scatters at 180 degrees. Why? Well, that would be the photon smacking right into this dead on instead of a glancing blow. And that'll send the electron forward fastest, which means when the photon recoils, it'll lose even more momentum than if it was just a little glancing collision like that. So that's the Compton effect. So that's our first topic in this, or first concept in this topic. Light bulbs actually send out tiny submicroscopic bullets that have momentum and energy given by these formulas, and we could calculate the energy, right, by plugging in frequency or wavelength, and then we could do conversion to electron volts. So that's our first video of the topic. I'll see you in the next video.